You are looking at a $10 billion time machine that will take us on a journey to the edge of the universe. A journey that will reveal how the universe looked just 100 to 250 million years after the Big Bang. A journey that will help us understand the formation of the first galaxies, and most importantly, a journey that will redefine our current understanding of the cosmos. You are looking at the largest and most powerful space telescope built to date, the James Webb Space Telescope. But why is everyone referring to it as a time machine? What makes Webb so exciting? And how is it a better telescope than the iconic Hubble Space Telescope that has already changed the course of astronomy? Don't worry, I'll explain everything. When you go to a place away from city lights and look up at the dark skies, you see stars, planets, a few galaxies, nebula, and most importantly, the Milky Way. But the universe is not limited to what we see with naked eyes. It's home to a wide range of frequencies that go all the way from gamma rays to X-rays, ultraviolet rays, the visible region, infrared rays, microwaves, and finally, radio waves. Thus, you can see that our eyes are limited to a very narrow part of the spectrum. The electromagnetic waves that we receive from distant stars and galaxies make up the most important way to study the cosmos. So, the question is, if our eyes can't see the entire spectrum, how can we explore the vastness of the universe? Well, this is where advanced telescopes come to our rescue. Although we've launched many space telescopes that work in different regions of the spectrum, Hubble is the largest and most versatile telescope of all. As a result, Hubble provided extensive insight into the universe, from objects as close as the Moon to the most remote galaxies. However, what Hubble studied was primarily at optical and ultraviolet wavelengths. In addition, it had some infrared capabilities. Still, when it comes to Webb, it's an infrared observatory that will mainly look at the universe in the infrared region, with some capacity in the red and yellow part of the visible spectrum. This means that Webb will help us observe even those distant areas that were out of Hubble's reach. But how can an infrared telescope offer a deeper insight into the universe's past than an optical one? Why are infrared observations so important to astronomy? Infrared radiations are nothing but an object's signature in the form of heat. Although we cannot see infrared radiation with our naked eyes, we can feel it. For instance, the heat from the stove in a kitchen is infrared radiation that we can feel with our skin. The electromagnetic spectrum shows that the infrared rays have a longer wavelength than the visible rays. Are you still there with me? The universe is full of regions that contain dust. Stars and planets that have just started forming also lie hidden behind cocoons of dust. Even when you look at the Milky Way, you'll notice dark dust clouds obscuring much of the galaxy. The problem is that stellar dust absorbs most of the visible light due to its short wavelength. This offers a hindrance in having deep insight into the hidden regions engulfed in thick clouds of dust. But as I already told you, infrared rays have a longer wavelength than visible rays. Hence, the infrared light can easily penetrate the dusty shroud to reach us. The James Webb Space Telescope will cover the wavelengths between 0.6 micrometers to 28 micrometers. This will help Webb look over 13.5 billion years back in time, thereby providing images of the first galaxies formed and observing unexplored planets around distant stars. Are you wondering why I am saying it will look back in time? Well, that's because light travels at a finite speed. For example, it takes 500 seconds for the light from the sun to reach us. That means the sun that we see is how it looked 500 seconds ago. From Earth, we can never know what the sun looks like in real time. That's how everything we see in the sky is how it was in the past. No one knows what the universe currently looks like. Space observatories are free from atmospheric absorption of infrared light, and offer a far accurate view compared to ground telescopes. However, there are several constraints by which infrared telescopes need to abide, and Webb is no different in this case. Infrared telescopes are specifically designed to minimize the amount of heat produced by them. Hence, Webb has to be kept at significantly low temperatures to make precise observations. Webb's mirror will be kept at a temperature of -233 degrees Celsius to shield it from the heat of the sun. In addition, the telescope has a 5-layer sun shield the size of a tennis court that will eventually weaken up the heat from the sun by more than 1,000,000 times. A successor to the Hubble and the Spitzer space telescopes, James Webb is expected to lead a new era of astronomical observations. The quest to see the birth of the first stars and galaxies has been a holy grail in astronomy for decades. Since we are made of materials once processed in the cores of giant stars, it's like searching for our own origins. If you're interested in studying astrophysics at home, make sure to check out our Basics of Astrophysics series, the link to which is given in the description. This series explains everything at the most fundamental level, from the EM spectrum to telescopes, and from the birth of stars to the formation of black holes and galaxies.